measurement, the Global Environment Measuring and Monitoring Initiative. And so I'll tell you about my contribution to that. It's a joint Berkeley-Stanford contribution to an international effort. Okay, so the story I want to tell you today is how we can think about bringing technology to understanding the air in cities, and to do that with a spatial mapping resolution that's never really been attempted before. But before I get to that, let me just say that this work is at the intersection of a variety of other atmospheric science activities in my research group. As Tom said, we're particularly focused on the role of temperature. And we have a paper that came out this week showing that high temperature events in Los Angeles are driving the high aerosol in Los Angeles in a way that was not true 10 years ago. So showing that the sources of aerosol in the city are different sources than they once were. We have using optical technology that a lot of you might be familiar with. We do a lot of work with reflected sunlight as observed in a UV visible absorption spectrometer in orbit. It's a 0.5 nanometer spectrometer with a 2048 CCD array at the back of that spectrometer. One dimension of that array is spectrum and the other is footprint on the ground. And we're using that in a lot of interesting ways to think about urban air pollution at the scale of the whole city. And then some other projects that look in mostly using laser spectroscopy in details of how plants in the atmosphere interact with the nitrogen cycle and how organic molecules and nitrogen molecules interact in the atmosphere to make aerosol. And like all of the things that faculty do, none of this happens without awesome graduate students and postdocs. And so the work I just told you about was led by Aaron Delaria and Brian Place, who's not in this picture, on plants, Chindan Zhu on satellite remote sensing, Hannah Kanegi on aerosol organic nitrogen, and Clara Nussbaumer on temperature in Los Angeles. But if I turn to the story I'll tell you today and its intersection, the intersection is really how we think about cities. And let's, instead of the air quality for a little bit, let's focus on the climate impact of cities. Cities are responsible for most CO2 emissions, and more people are living in cities. So you can see by 2050, we're expecting half or more of the people on the planet to live in cities. If we say, above 100,000, so that's about half. And you see over here that something like 50 to 80%, depending on how you count, the CO2 emissions are driven by cities. In the language of our economist friends, scope 1 emissions are emissions that happen in the place where you live, and scope 2 emissions are emissions that happen somewhere else because of the consumption where you live. So let's just bring that example and let's look at a specific city. So Oakland, across the bay from you, is about a little less than 500,000 people. And the Bay Area region we share is 8.7 million people. And the state has a greenhouse gas plan, and that greenhouse gas plan is expected to bring us along this top line here. So that will be about half the total emissions from the city of Oakland if the city does nothing on its own in 2050. And the city has a plan to add to that and reduce CO2 emissions further and bring us along this line. So that would be about 10% of current emissions by 2050. This is a challenging thing for cities to do and show that they're doing it right. Here's a recent paper from Kevin Gurney at Northern Arizona University. He's got a strategy he calls Vulcan, which is a way of calculating emissions from all the different sectors that contribute CO2 in every city on the continent. And then he went through and he took the individual analysis by each city that made it publicly available, compared what they observe to, or what they say their emissions are to what a uniform story is. And not necessarily that the uniform Vulcan is right, but it's a reference point against which you can compare. And you can see that there are cities that are in pretty good agreement. So here, for whatever reason, San Francisco, Oakland, and maybe Fremont are in good agreement. Vallejo looks way off. This place in the South Bay looks off. All of them ostensibly trying to calculate their CO2 emissions for the same kinds of emitters in the same way. So what we'd like to do is we'd like to be the observational constraint that allows everyone to move to something that's demonstrably accurate, that they can agree on, and that provides the sort of public feedback that says to the political sphere and the public sphere, the contributions you're making to reducing emissions are happening the way you intended and for the reasons you intended. And I should say, so let's look here at Oakland. By this measure, Oakland looks about right. And then if you go into the details and say, look at Gurney's inventory, Oakland is 50% different than that inventory in the off-road transportation. It's 15% different in the opposite direction for stationary sources. So it happens to be in agreement with the national prediction for what's probably not the right reasons. So Beacon then is our experimental approach to trying to bring some observational detail to this analysis, and to do it both city by city and sector by sector. So separating what's happening in the large buildings from the small buildings, separating what's happening along the bridge and the major highways from the inner city streets, and so on. And the experiment looks like this. There are 75 nodes in the network: the Beacon Environmental Air Quality, Berkeley CO2 Observation Network. If you're bored while I talk, you can go to this website and see the CO2 concentrations that we're observing today. They show up every hour in more or less real time across most of these locations. And this is, as the other things I showed you, this is a big team effort. So Aaron worked on calibration of the sensors, and Kevin worked on the website and the database that makes this all work. Helen and Jinsal also worked on the experimental efforts and the calibration, and Alex Turner worked on the inverse modeling. And in combination, we're able to tell you some things I hope you'll find are sort of interesting about what we can learn about urban emissions. And really what I'm talking about is a system to understand the air in cities that has three parts. It starts with the ability to make predictions for what we would observe, some hypothesis, and that combines the economic data of the variety I showed you that cities are gathering, and in Kevin Gurney's model, also the social data, who lives where and how much they drive and so on. And it links that to the weather, since what we observe is concentration at a moment in time, and that concentration is affected not only by the emissions, but by the winds. And then we have an observing system. In this case, it's a sensor network with spacing of order 2 kilometers between the nodes, and some strategy for interpreting those observations that synthesizes these two pieces. In this case, it'll be in the form of an inverse model that allows us to go back to the beginning and iteratively improve these parameters so that we have an understanding of what the emissions are. So let me just tell you a little bit about each of those pieces. So in the Bay Area, the estimates of urban CO2 look roughly like this. It's about a third from the transportation sector, a third from the industrial and commercial sector, about 15% from electricity, and then the balance from some other small things. And so that's the total, and then we can put that on a map, and the map will have both the location where those emissions happen and the time. And so here we have what you see in the middle of the night at 2 a.m. in the map, in this inventory that we put together. You see all the point sources from the industrial emissions. This crop up here, mostly the oil refineries, many of the others, power plants, but some other ones. Alex's favorite one on the list is the Jelly Belly factory. That's about the 150th largest point source in the region. And then in the morning, you can see that the vehicles start to compete with the point sources. You know, as you would expect, because what we said is roughly the industrial sources and the vehicle sources are comparable. That's a start, but the other thing we want to know, not just the total and the location, but we want to know something about the processes. So for example, how fast is the vehicle fleet being electrified year over year? And is that driving changes in CO2 emissions? Are our CO2 emissions from the vehicles, are they different when we're going fast and when we're going slow? And so on. So let me start here with a movie and just give you a sense. This is sort of the summary of what I've told you so far. You create some estimate of the CO2 emissions, and then you move them around with the winds, and that's your initial hypothesis. And then imagine that you sprinkle this grid in the model with observations, and we want to do some comparison at each grid cell with the predictions. And so we've set up, that's a 1 kilometer grid. And we've set up to be on about 2 kilometer resolution with our observations, and hoping that's enough to capture the important details. Okay. So here again, those observations. And this is an idea that we've been trying to explore. The idea is that having really high spatial density, and in this case, a map where we have 1 observations every 2 square kilometers, allows us to approach this problem with what in the language of the CO2 world is a small footprint. So imagine if we had 1 measurement at a really high location downwind of the city that effectively integrated all the air that came from the city. That would be some large footprint. We'd get on average sampling the whole city. And here instead, each location is very strongly influenced by its nearby surroundings. So we're approaching this by many, many small footprints. But every piece of air does come from somewhere else further upwind. So along with the local footprint, it's got some exposure to the larger region around it. And the interpretive challenge is to integrate those 2 different spatial scales. But the other piece of this is to use the statistics of large numbers in interesting ways. So large numbers of sensors should overcome biases in any individual location. If we've made a bad choice about a spot to put a sensor and we only put out 3 really good ones, then we're very, very driven by the location. If we put out 100, then if a few locations are lousy, then it doesn't matter so much. And also the square root of n should help. That if the sensors have a rough uncertainty of 1 part per million in CO2, and for context, the average concentration is 400, that would be equivalent in a regional mean roughly to 1/10 of a ppm, just the square root of n advantage. And we get a map. And there are lots of other aspects of this problem where we think that the large numbers allow the statistics to overwhelm bias, error, and uncertainty. Okay, so what's in these nodes? So in each node is a CO2 sensor. The CO2 sensor is an optical sensor. It's got an infrared light source and a Fabry-Perot filter. Along with a multipass cell. The Fabry-Perot filter allows you to choose wavelengths where CO2 is strongly absorbing and then shift off of those and measure a background. These 4 gases are all electrochemical measurements, and then there's 2 optical particle measurements. We bring aerosol flows into the box with a small fan, and then it finds its way to the 2 particle sensors, and they measure the number of particles by light scattering. And you can see just examples of what those look like here. These are commercial parts that are integrated into this package. So the sensors are then placed all around the Bay Area. The 2 that I show you here are ones on the roof of the Exploratorium Science Museum. We have a strong and long-going collaboration with them. You can see a display of our observations, and especially of these 2 inside the museum, and in connection with all these other measurements that the Exploratorium is making on their roof. So step 1 was to have a strategy for driving the cost of the instrument down low enough that you can have a conversation about having 100 of them. The project is not low cost if then you couple that with really expensive labor and time-consuming activities. So part 2 of this is identifying strategies for maintaining quality control and calibration with a low level of effort. We've done this in using a number of different ways, and I'll just give you a sense of them here. The rough assumption is that the sensors are linear, so that the gas, the target in this case, can be expressed as the measurement multiplied by some factor with some additive offset. So for example, carbon monoxide is 100 parts per billion per milliamp times the current measured minus some offset. The calibration and the offset vary in time, and we may need to have additional parameters where they depend both on the temperature and the humidity. So we may need to track several more parameters per sensor. So that's the idea. So we're going to imagine that we have inside this collection of measurements and equations and unknowns that constrain these variables. And the idea is to do that from the observations in the field, not have to bring gases of known concentration to the measurements. So as an example, some relationships among the chemicals are really well known. At night, if you have high nitric oxide concentrations, you can't have any ozone because the NO reacts with ozone to drive it to 0. So that if we look through the observations and find times when NO is high, we can set the ozone instrument to 0 at those moments. The other idea we employ is that occasionally all or large regions of the network sample identical air. Nearest neighbors have to mostly look like each other, at least on some time scale. And when we have them, we use more accurate references in the domain and tie some moments in the observations to those more accurate references. So the strategy is to then find the optimal combination of all of these different constraints to produce a set of observations that are good enough for the science questions we're posing. So here are the examples, and they're described in these 2 papers. Here's measurements of NO2. In blue, the measurements from our electrochemical sensor. Red measurements in the same location from a device that was not used in the calibration process at all, so entirely independent. And you can see that the precision is of order 5 ppb, and we can see the ups and downs modestly well, and for our purposes, that's good enough for the studies we're interested in. Here you can just see that same thing for the ozone, the carbon monoxide, and the nitric oxide. You can see the nitric oxide and the carbon monoxide are more precise in their overall better measurements than the other 2. For CO2, we've done a lot of work trying to understand the accuracy of the calibration. Here's one example of trying to understand what it is to look at the differences of every sensor with its nearest neighbors. And on average, that difference can be summarized as having a standard width of about 0.007%. I mean, or fraction 0.007. Okay. So let me just show you that what we get is a map and a time series of that map. So here's an example from a couple of years ago of aerosol from this network. And you can see that the aerosol goes up and down. It was sort of uniformly high for a moment there. And you see again, getting higher at that time of day. And then similarly, here's the CO2, and you can see it gets high and then gets low again. Okay. So the next thing that we want to do is we want to collect all those observations and our initial guess hypothesis and bring them together. And the example I'll give you is the example from a year ago today, more or less, when we had the first of the COVID-related shutdowns. So right here, March 17th. So you're seeing in this long time series two effects. You're seeing that right here in this window here, the effect of the COVID-related shutdowns dramatically lowered emissions into the Bay Area. And then on the longer time series, you're seeing the seasonal cycle of CO2 and of the atmospheric boundary layer mixing so that the data set gets quieter and cleaner in the summer than it is in the winter when there's much more stagnation and those higher concentrations at night. I should say all of these highs are at night. It's kind of a curious thing that you see high concentration at night, even though the emissions are much lower. And that's because the atmospheric mixing is much lower at night. So the first part of this is to take the weather model and combine it with all the observations and identify the region of influence. And so that's called calculating the footprint. And we worked backward from every measurement and every one of these yellow stars. And we ran a weather model backwards in times from that location and asked where was the last time the air touched the surface of the earth. And when you do that, 40% of the total influence on the network comes from within this white outline. And so we consider this to be the region that's well constrained by the observations. You'll see that, unlike some other part of the world where the wind changes direction a lot, even though we have observations here, we're essentially insensitive to observations just a couple kilometers away on the other side of Vallejo, because the winds are always from the west. So the first example of the story I'll tell you here is to say, how much did CO2 emissions drop in the early phase of the shelter in place, and why did they do so? So here's that same set of observations I showed you. Now with the two time periods we'll compare marked in purple and green, before and after. And the fact that spring came and the weather changed will account for using that weather model. So that'll be taken into account. And here's what we know happened in the environment. We know that cars and vehicle traffic dropped dramatically. Both cars and trucks, you'll see that measured here in red before the pandemic shutdown. And you see there were on average, say 6,500 vehicle miles traveled, or 66.5, 10 to the fifth vehicle miles traveled inside the footprint before, and then those dropped in the middle of the night down to about 1/10 of the fifth. And then after the pandemic, the peaks are more like 5 or 4. There's a much stronger weekend peak. Some people still went to work, but almost no one was driving on the weekend by comparison. And even lower numbers at night. You can see that the truck traffic also dropped, not exactly in the same ratio. And trucks have a very strong, they're off the road on the weekends, and even more so during the pandemic shutdown. If we integrate across the whole, just to get a sense, here's what the CO2 looked like by day of week, before and after. You can see that, relatively speaking, the weekends are more subtle. Weekday rush hour is a very strong effect. But you know, all times of day during the week, we had significant reductions. So what we do then is use this sophisticated Bayesian inverse analysis to make the connection between the observations and our initial guess. And I won't go into the details on that modeling, but just tell you the results here. The results for emissions before the shelter in place, expressed as tons of CO2 per square kilometer per hour. These are 1 kilometer pixels, more or less, so tons per hour in each of these pixels. And you can see the big change during the shelter in place. So you see here that the car is going into the Bay Bridge from either side, dramatically lower. You see that it's lower here in this region of the North Bay highways, but more subtle. And here you see that as the difference, you know, very, very large changes on 880, this feeder into the Bay Bridge, smaller changes on this highway up here, and differences in different locations. So the beacon network is giving us this map of where the changes happened with exceptional fidelity, and showing us that the changes were not uniform across the domain. Again, if we add them up, so I've put in this red line as a reference here for you. That red line is 400 tons of carbon per hour. So if you look at that here, so here you can see that before the pandemic, the total CO2 emissions were always above that red line. And during the deepest part of the shutdown, almost never above that red line. And you can see the orange is vehicles, and vehicles are what changed. More than anything else, the inverse model and the observations are saying that vehicle emissions dropped by about 45%. Total emissions dropped by about 25%. And it shows that there were some reductions on the weekend, but they're more subtle. And you know, the other interesting and exciting thing about this is we get very strong information about time of day. So we had significant emissions at night before the pandemic, and essentially none after. So that's a big change. There's a little bit of a signal from the biosphere. In this case, the signal goes the other way. So the forests around the Bay Area take CO2 out of the atmosphere. They're not insignificant compared to the emissions. In this case, we constrain them by using measurements from space, but we think we could go back and let them run free and still identify them. So it's interesting to start asking the question, well, how correct is this analysis? So what we did here is we just normalized the midweek daytime emissions to 1, and then compared everything to that reference point. So blue is the beacon inversion, and red is counting the number of vehicle miles on the roads from Caltrans. And you can see there's a pretty exceptional correspondence. So that most of what we're seeing is a change in the number of vehicles on the road, and that looks similar, but maybe not quite as good on weekends afterwards. You know, and again, you know, the other thing that we have here is not only the total, but the map. And the map is really interesting, and here's just one example. If we look at those traffic counts and ask, how are we doing? In the warm colors here, you're seeing places on the map where the beacon inverse says the emissions from vehicles decreased by more than the Caltrans vehicle miles traveled. And in blue, places where the answer is less. So it's not a uniform agreement between the number of vehicles on the road and what we're inferring. We're getting disagreements on both sides. And that brings me to the second question. So the fact that everything didn't change in sync made us start to think that the inverse model was giving us information about processes related to driving. And so my graduate student, Helen Fitzmaurice, has been looking into whether speed could be explaining why we see differences of both sides. So let's just we'll look at one segment of road, this stretch of 80 that feeds the Bay Bridge or goes away from it, depending on which way the traffic's going. You see here speed in the two directions, red one way and blue the other. I apologize, I forget which is which, but I think the really low speeds that are blue are approaching the bridge in the morning. And so you see in the rush hour traffic before the pandemic, vehicles are going often as slow as 20 miles an hour one way, and they're slow the other way too. They're 30 miles an hour. In the middle of the night, they're almost always going 70. And then after the shutdown, the traffic is almost always free flowing. So the rush hour traffic drops from the nighttime 70 to 65 or something. Hardly any change in speed at all, and fast. And if we look at what we think we know about fuel efficiency, when we're moving like this at 20 miles an hour, we think the average car gets 14 miles a gallon. And over here, it's sort of the typical midday speeds of 40, 45, 28 miles a gallon. And then at really fast speeds, we think efficiency drops again. So we shouldn't, if we understand things correctly, get a simple correspondence between vehicle miles traveled and CO2 emissions. That should be convolved with how fast they're going and the average fuel efficiency of the fleet at that speed. And just to give a sense of what this looks like in a prediction, this is a prediction of using the mean fuel efficiency for the vehicle fleet by day of week, and then something that's on average 3 miles an hour slower or faster. And we don't think you know the efficiency of the vehicle fleet to within 2 or 3 miles an hour. That's one of the unknowns that we have to derive from the observations on road. So let's just take a little look at what we can get in some other comparisons along these lines. Here's think of this axis going from high fuel efficiency. So at 28 miles a gallon, the CO2 per vehicle mile traveled is relatively low. And then up here at 17 miles a gallon, the grams of CO2 per vehicle mile traveled relatively high. This is what we would predict based on Caltrans data and the speed and our sense of the kinds of vehicles and their average fuel efficiency. And this is what we infer from the Beacon inverse model, matching pixel to pixel. And you can see that for the Beacon inverse is more linear, so closer to this model than the prior guess. I don't want to say that we're fully confident of this, but it's encouraging that there's information contained in the Beacon analysis about fuel efficiency versus speed. And I just to show you, I drew a line through that, and you can see that a line through the black points wouldn't be quite in as good agreement with them. Just what we're seeing here is a move in this direction is the inverse model inferring either a different number of vehicles than went into our initial guess or a different speed. This prior is not the measured number of cars at that time. It's the number of the typical number of cars at that time. So we'll have to take some time to go in and adjust this to use the actual number of cars on each day to try and separate the number of vehicles from their fuel efficiency with speed. Okay. So what I've shown you here so far is that we can get pretty rapid transition from observing emissions changes to reporting them. I didn't point out the paper as I went by, but we made these observations. The last ones we used in the analysis were in May 2020. They appear in a publication in November 2020. So we've demonstrated one cycle through the analysis that can be pretty quick, and we could do that routinely, both in a scientific sense, but also in a supportive public policy that might not require the end result being a peer-reviewed paper. We have the beginnings of a strategy for talking about attributing emissions sector by sector, industry different than passenger vehicles, different than trucks, different than home heating, doing that with timing information, day of week information. And you saw in what I told you that day changed differently than night and weekends differently than weekdays. And finally, what I showed you is a 25% change with 12 weeks of data. So I can tell you that doing a 12% change in 12 weeks would be easy. But the climate action plan that I showed you for the state and for Oakland, they're planning changes of 3 to 5% per year. And what we haven't yet shown is that we can measure changes at 3 to 5% as in cities we move to net zero CO2 emissions. We think we can get there, but that hasn't been technically demonstrated yet. Okay, so let me turn back just for a moment to the 5 other things that we measure. So here's an example that's more about air quality, but it's connected. In the top, again, the CO2 observations I showed you before and after the shelter in place. And then in the bottom, the carbon monoxide measurements. Carbon monoxide decreased during the pandemic by 30%. And that's right now, CO mostly comes from passenger vehicles. And so that's what we're seeing here. So just to wrap up, what I've tried to give you a flavor of is an experimental approach that uses a range of technologies brought together in a small package to map emissions at scales of individual neighborhoods, to do those in a dense networked way where we combine the information across the whole network to learn things about local emissions and regional emissions. And the way that we do that combination is with inverse models, and alternatively, you could imagine strategies for direct analysis and data assimilation to other sort of standard methods that we and others have used to interpret these kinds of observations. So finally, we're excited to be expanding this idea and bringing it to other locations. So in the Global Environmental Measurement and Monitoring Network is supporting collaboration that we have with the University of Strathclyde. You see there a map of the city of Glasgow, where the next meeting of the parties to the CO2 treaty, COP26, the Paris Accords. That meeting will happen in November. There are 25 nodes sitting in an office in Glasgow, waiting for their lockdown to be lessened a little bit so they can go out and do installations. That they have the permissions already and they're installing. And then Will Barrelson at USC is going to install a set of nodes that are north and then east and west of the USC campus. USC is right about there. And so that's going to be another strategy for expanding the number of people thinking about how we can use dense networks to learn about greenhouse gases and climate. So finally, let me thank the grad students who work on this project with me and the staff, Catherine Newman and Paul Wooldridge, Alex Turner, who did the inverse modeling. He's now at the University of Washington as a professor, and the rest of this really amazing team I get to work with. And thank you for your attention.
Thank you very much for your talk, Professor Cohen. At this time, we will start the Q&A portion, and so Rebecca is going to take over to moderate. As a recap, please react with either the green check mark or raise hand or type your question in the chat box.
Okay, Professor Bayer has a question.
Yeah, Ron, thanks. It was a great talk. And just curious, the other greenhouse gas that are attributed to significant climate change is methane. And I was just wondering if you have any comments on what contribution you think that is making to the overall GHG emission from urban environments, and what's the probability that we'll have sensors that could be deployed in your packages that would measure methane?
So methane is an important player. Its emission pattern is really different. Its emission pattern in cities is primarily driven by the distribution of natural gas and leaks at switching stations and valves in the natural gas system. So the most effective strategies for quickly catching those leaks has been to drive around with a state-of-the-art instrument instead of doing some mapping. Over time, that might change, and we might shift to more distributed sources, needing to understand landfills and other methane sources over longer times. And then it would make sense to have a network sensing strategy. The cost, both for managing point sources like industrial facilities and oil and gas drilling for sensors, has been coming down. The strategy of choice is a mid-infrared tunable laser, and with some coupling to a pretty long optical path length. And we've seen a variety of different technologies along those lines, driving the price down to maybe $5,000 an instrument for methane. So that could conceivably come down further.
Okay, great. And Leo has a question.
It's great to see the nice results and all the information you've been able to extract from the sensors. One thing that struck me as interesting in the pre-pandemic and post-pandemic, or during the pandemic, the change in the vegetation on one of your plots seemed bigger than I would have guessed. Is that just change in seasons or something else?
Yeah, you're seeing this seasonal cycle of CO2.
Okay.
Spring comes in the Bay Area early. If I showed you the same, we had done that experiment on the East Coast, there would have been no change. It would have been quiescent in that period.
Okay, thanks.
I actually have a question. I was wondering, how long does one of those boxes last? The nodes, I think you called them.
Yeah. So our experience is the box lasts until some aspect of the communications hardware fails. So that tends to be the weak link. And it wasn't what I expected would be the weak link going into this. Like a lot of you, I build instruments, and I always expect the measurement device to be the weak link and the telecom things to be easy, but it turns out not to be true. So we started this idea about 8 years ago, and we started trying to use a plug-in Ethernet strategy on the roof of buildings. And then we went to a 2G telecom strategy. That ended up being challenging instrumentally and extremely challenging bureaucratically. It's just incredibly time-consuming and complicated to pay a monthly bill, even if it's small, and more so when there's 70 locations. So we went back to a wireless strategy now that almost every school and almost all of these nodes are on the rooftops of schools. So we have wireless communication. So for nodes where we have good communication, we're getting 2-3 year lifetimes. In places where in places where we don't have communications, then we find that other things break when we're not watching as well.
Thank you. And Derek has a question.
Yes, thank you very much for this very interesting presentation. Regarding instruments, are you considering introducing new types of instruments in the future? I was thinking of satellite observations or others. And my second question is regarding precision. Could you get eventually maybe weekly averages at maybe 1 ppm measurement for CO2 over your region of influence to keep some continuous tracking of scientifically verified volumes? Simply, the question is, that would be very useful to then actually connect to economic instruments. So I was just wondering if that type of trust could be achieved. Thank you.
Okay, so we and our community are very involved in various kinds of satellite remote sensing. In my case, I'm much more active in satellite remote sensing of nitrogen dioxide than CO2, but there's a very large and active community looking at remote sensing of CO2. Just to remind you of the challenge of CO2, your other question said 1 ppm. So remember that CO2 has a rough concentrations of 400 ppm. So when we ask for 1 ppm accuracy, we're asking for precision of a part in 400. And that's just hard even with really good instruments if you're not bringing a calibration gas to the instrument on a regular basis. I do think that we are on average good to about 1 ppm, maybe better. We have a well-calibrated higher reference infrared laser system in the domain of the node, all the nodes that we're using as a reference point. So that helps us stay on track with a calibration. So I think one could create an average at whatever timescale was interesting across the network.
Thank you.
Rebecca, I see a question in the chat. You want me to answer that?
Yeah, that would be great. Thank you.
So the question in the chat is, what's the price? And the price is about $8,500 per node of cost to us. And then depending on how we do it, the university indirect costs on top of that. And the other part of this question, is there a possibility of outsourcing this to people who would do it themselves? The reference here is to the Berkeley earthquake measurements. So that I think those of you interested in this might take a look at a company called Purple Air. They're selling an aerosol instrument for a couple $100 that has incredibly widespread adoption in the Bay Area, and you can get maps with much, much better coverage than we have. I think the scientific community doesn't know whether there's a real advantage for going to higher density. And so I think it's a really good question. There are CO2 sensors that are 10 times less costly. They're interesting. They have a similar optical path length. So their short-term precision is identical to what we have. It's their long-term accuracy that's hard to track. But it would be really interesting to try and imagine a distributed network that was created by consumers at a price point that's much different than this, at a few $100s. We haven't been interested in pushing that, but I think it would be it's a really interesting idea. You could imagine that going forward somehow. And the Purple Air is a demonstrated example of that. Oh, and the last question from Keith is, any more comments on methane? So I think methane is really just a price question. It's a price and ease of use question. So we know how to make measurements of methane really well. A high resolution infrared laser mid-infrared laser does a great job. And so the challenge is maintaining a calibration over time. I think that's doable. And the other challenge is building a mid-infrared laser package coupled to appropriate, multi-passing and a detector that's at a price point that can change the economy of how they're used. So right now they're used by people who want to have one and are willing to pay a high price because the labor costs for their using the sensor are high compared to having one at $5,000 or $10,000. And so if you wanted to change that where the same labor costs could use 20 or 30, it's really just changing the ease of use of those instruments and maintaining the calibration. And so it's how do you get the cost of 20, if you could get 20 or 30 for $150,000, someone might do that if they thought that the same one person who might put an effort and use one could keep track of 20 or 30. And that's a hard piece, and no one's done the work to show it's plausible, but it seems like it should be.
There's another question from Keith on the chat,
Sure.
or a comment, sorry.
It's a question, so I'll read it. So the question is that CO2 measurements in building control systems reset the baseline every night. And it says, our data suggests this strategy is fundamentally wrong. I think the question is one of scale. But yeah, the CO2 from outside the building is much, much higher at night. So if you had a building with no occupants in the day and the daily cycle of CO2 in your building was not driven by people, then you would want to reset the zero of the CO2 instrument in the daytime and not at night when it's higher outside. But if you're in a situation where your CO2, the daily cycle of CO2 in your building dwarfs the CO2 cycle outside, then you would make different choices. And that's really the question. I would say if in a lot of building control systems, they should be measuring the inside and the outside. Because they have many, many CO2 sensors inside the building to track the controls, and they'd only need one outside. It wouldn't change things very much. And then you'd be able to set at any time and day that's optimal for the low building occupancy. You'd set to be the same as the outside one.
And we have a question from Jason.
Hi, I was curious why some of the gases are monitored with electrochemical sensors and others with optical sensors.
So it's basically price. In most of my work, I use an optical sensor for NO2. It's 1,000 times more sensitive than the one I showed you. But that one is $150 or $200, and it's good enough.
Thanks.
Okay, so we have about 1 more minute. If anyone has any other questions, now would be the time. Let me just double check the chat.
Just to comment on Jason's question, isn't it easier to do ChemFed on a reactive chemical species? Doesn't that enter into a little bit the choice too?
So I don't know if it's easier. You could imagine some people are using sensors for hydrogen. I don't know if you want to call that reactive. So I think it's the trade-offs between an optical sensor and a redox sensor are, a lot of them are signal to noise and operational, and so you could have the NO2 absorption is strong enough, you could conceivably do something optical.
Well, Rebecca, I think we can probably cut off the Q&A, and I think it's time to thank our speaker once again, and thank you and Jason for helping organize the seminar. So thanks, Ron. A terrific talk.
Thank all of you for having me. Appreciate it. Get a chance to talk to you. And feel free to send me a note if you have any questions you didn't ask.